Thank you. All right. Sorry, Chris, for the slight technical problems here. Anyways, it's my great pleasure to introduce today's speaker, Chris Vale. Chris is from the Center for Quantum and Optical Sciences at the Department of Physics and Astronomy at Swinburne University in Australia. So he's actually speaking to us from the future, since it's already his Friday morning over there, right?
Correct, yes.
Awesome. I hope Friday is going to be a good day for us. Anyway, so Chris got his PhD in physics in 2001 from Victoria University. And from 2000 to 2002, he was a postdoc at the University of Sussex in the UK. Then he became a research fellow at the University of Queensland in Australia. And since 2007, he is senior research fellow and professor and ARC future fellow at Swinburne University of Technology. That is in Melbourne, right? French Opens, right? No, Australian Opens right now taking place out there, I think.
Correct, yes.
All right, I've been in the news. Chris has got a long history of excellent work in the area of ultra-cold atoms. He's at Sussex and at the University of Queensland. He was working on atom chip technology. So the idea is there to take currents on a computer chip and to have ultra-cold atoms guided by the magnetic fields that these currents actually produce to make flexible devices like interferometers and all these things. And when he moved to Swinburne in 2007, he started building up a Lithium-6 machine. Now, Lithium-6 is very interesting because it's a fermion and it allows you a very nice access to the BCS-BEC crossover. So you can do BCS physics that's similar to superconductors and connected to the BEC side where we have got our usual BECs. And he's very well known for actually his precise measurements of excitation spectra of strongly correlated fermions. We actually have followed his work since many years. It's very nice stuff. More recently, he's also started working with isoprosium, which, as we know, is very interesting because of its magnetic properties. And it's got like 10 new Bohr magnetism, which means you've got long-range interactions, dipole-dipole interactions. And that he's doing as part of the ARC Center of Excellence for Future Low Energy Electronics Technologies, or in short, HEAT, where he investigates concepts related to non-equilibrium physics and topological phenomena. And maybe this will one day also find applications for the development of future 2D materials. So it's really a very broad area. So we are very happy for that he is here. And yeah, please take it away. Thank you very much.
Great. Thank you very much, Peter. That's a very kind and generous introduction. I'm very grateful for that. I have to say it's a real pleasure and honor to be able to speak to you today. It's I know it's very difficult to run these sorts of event colloquia and seminar series. So I appreciate the efforts and the invitation and opportunity, and hopefully one day in the not too far future we'll be able to do these things in person again. So can I just check my audio is coming through okay? The levels are clear and yep, okay, great.
Okay.
All good, excellent. So yeah, today I'd like to talk to you about some work that we've done at Swinburne, which is in Melbourne, as Peter said, and there's quite a few people that have been involved in this work. So there's the experimental team, most notably Paul, Andrew, Ivan and Alan in this list here have contributed strongly to the experimental work that I'll talk about. And we've also had some very nice collaborations with theorists in the Netherlands and France and also Italy and Queensland. So this is quite a large number of people involved in this work, but it's been a lot of fun. Okay, so I thought I'd start off today, or start off the seminar with a bit of an introduction to where I'm from and you know, a little bit about life in Melbourne, because it's obviously quite a way removed from where you guys are in Washington State. But and particularly these days when travel is so difficult, you probably heard that Australia likes to keep its borders very, very tightly closed. But hopefully this will be changing again, and we'll be all able to move more freely soon. But to give you some perspective, where I am in Melbourne here is essentially diagonally across the Pacific, if we imagine flattening out the globe from where Pullman is. And according to Google, we're less than 24 hours away from each other. So it doesn't sound so far, but somehow in these last 2 years, it's felt a lot further than that. So Melbourne, a little bit about Melbourne itself, it's kind of known for being an international sort of cosmopolitan city. We have about 5 million people, quite a multicultural city, and also known for our food and coffee culture. And in fact, again, if you ask Google, for example, what it rates as the best coffee cities in the world, Melbourne usually appears fairly high up on the list there. So that's one feature we're all very proud of, and we're all fortunate to enjoy. So there's lots of good things about Melbourne. However, the past 2 years hasn't been all good news. If you do another type of Google search and you look up what is the world's most locked down city, or what's been the world's most locked down city, Melbourne also takes most of the headlines there. So through the pandemic, we've actually spent 262 days officially in hard lockdown, which means it's been a very quiet and fairly dreary looking place to be. So I don't think we'd be winning any titles for the most livable city in the last couple of years. But as we know, hopefully things now with high vaccination rates are going to resume some sort of more normality, or fingers crossed anyway. We don't want to get ahead of ourselves at all in this pandemic. But yeah, this is that's a little bit of a view of life from Melbourne, with a particular focus on the last couple of years. Okay, so now I'll move on to the science, or the physics content of the talk, and begin with a bit of an outline. So as Peter introduced, we spend a lot of time looking at studies of strongly interacting Fermi gases, so ultra-cold gases of ultra-cold atoms cooled down into the nanoKelvin temperature regime, where we use fermionic atoms, and we can tune the way that the fermionic atoms interact with each other. And through that, we can achieve this so-called BCS to BEC, or Vale-Cooper-Schrieffer to boson-Stein condensate crossover, which we can do essentially by tuning the strength of attraction between a spin-up and spin-down fermionic particle. And so these systems are interesting for a number of reasons. There's related problems that appear in nuclear physics, in condensed matter physics, and in some aspects of high energy physics as well. But because they're a kind of laboratory-based experiment where we have access to control a lot of the parameters of the experiments, it means we can test things in a way that we can provide benchmarks for theory, or facilitate quite easy relatively easy comparisons with theory. So it's gives us a chance to work closely with theorists on certain aspects, which is really nice. So the work I want to talk to you about today is actually looking at some aspects of what we could call non-equilibrium physics, and that is how a system of fermions responds to a quench of one of the parameters of the system. So we have our gas of atoms, and then we suddenly change one of the parameters, and then we're going to look at what happens to the cloud, how it responds, and what we can learn about the cloud, or about the system, by looking at how it responds. So there's basically two experiments I want to talk talk to you about today. One is quenching across the normal to superfluid phase transition. And the second experiment will be looking at exciting what's called the amplitude mode in a superfluid. So this is basically an oscillation of the order parameter, or the amplitude of the order parameter of the superfluid. So I'll try and explain those two a little bit more as we go through. Okay, and I'll also say that if you want to ask questions at any time, please do, but at the same time, if the format is such that you prefer to keep questions till the end, that's also fine. So feel free to interrupt is the message if anyone would like to. Okay, so just a bit of an introduction to non-equilibrium phenomena in physics in cold atoms. So we're all well aware that the universe around us is very much a non-equilibrium system. And that's where a lot of the most interesting problems lie, for example, in biology, chemistry. Think about dynamics in cells. There's a lot of non-equilibrium behaviors that are happening there that are really important for understanding the world around us and understanding these systems. In our field, we're perhaps more interested in aspects of non-equilibrium phenomena related to quantum matter. So quantum materials such as cold atoms or topological materials or superconductors or other situations where quantum features become manifest in a large macroscopic type object. These are actually very topical these days because, for example, things like effects like optically induced superconductivity, these are sorts of phenomena that we might look to implement in some sort of future quantum technologies. But really, we need to have we'd really like to build up the sort of basic fundamental understandings of these phenomena to be able to use them as best we can. However, these are also very complex things to understand. So from a theoretical point of view, non-equilibrium phenomena means taking account of quantum correlations and dynamics that span very different length scales and also very different time scales. And that means that this presents challenges for theoretical descriptions, even in closed systems. And so this topic has been quite important recently in terms of trying to understand dynamics in quantum systems or in more complex quantum systems. Cold atoms, as I said, are nice in the sense that they can serve as a model system for trying to study different phenomena in a quantum setting. So, for example, cold atoms have been used recently to look at things like many-body localization, universal dynamics following a quench. So, how or some universal features in the momentum distribution, etc., that appear in dynamical systems. We can also perform flow-K engineering, where we periodically drive a system and achieve new states that way, or even look at the behavior of defects following a quench and observe universal features. So, for example, it's a very nice experiment from Yong-Il Shin's group in Korea a few years ago now, where they studied the number of vortices generated when they quenched from, or when they performed a rapid temperature quench to cool into the superfluid phase, and they were able to see that the number of defects or the number of vortices they produced followed this Kibble-Zurek scaling law. So again, seeing these universal type features appear in dynamical systems. So there's plenty of opportunities for studying non-equilibrium phenomena with cold atoms or other quantum systems, and so this was a motivation for us to start looking at some of the some experiments where we can do something or learn some new things. So I want to say a few words now about the system that we study before I go into the details of the experiment. So the system that we're going to be, or that I'm going to be using in our experiments, is basically a gas of lithium-6 atoms. So when I say a gas cooled to nanoKelvin temperatures, I mean it really is a gas. So we keep the system very dilute such that it remains a gas down at temperatures in the nanoKelvin range. So we use lasers and evaporative cooling, sort of standard techniques to reach these ultra low temperatures. I'm not going to talk about how we do that today because that's probably a topic for a separate colloquium in its own right. Just to say that we can make these systems. Typically, we prepare gases where we have an equal number of atoms in two different spin states. So for simplicity, we'll label one as spin up and one as spin down. And the atoms in these states interact with each other by the van der Waals potential, which is a short range potential. But because we're at very low temperatures, the de Broglie wavelength of the atoms is much larger than this R0, which is the length scale of the van der Waals potential. And it means that we can treat the interaction as a kind of contact interaction or point-like interaction. So the collisions are generally isotropic. We only have to, we consider a wave coming in and scattering off a point-like object to understand how the particles interact with each other. And that means that we can parameterize the collisions by a quantity known as the S-wave scattering length, which we call A here. And having access to what's called a Feshbach resonance means we can tune this value A over essentially a complete range that we would want to look at. And so this scattering length A really tells us about how strongly the particles are interacting with each other, whether it's an attractive or a repulsive interaction in the case of free atoms, or we can basically use this tuning of the scattering length to produce from a weakly attractive gas to a bound molecular state for a certain strength of interaction. In fact, I'll show you the next slide to explain that a little bit. So using this, what we call a Feshbach resonance, we can tune the effective interaction between two atoms. And I like to use this picture here to kind of give it's a very simplified picture, but it gives conceptually what's happening when we tune the interaction between atoms. So if we think of the case where we've got a negative scattering length, so that is the asymptotic value of the wave function comes down here and would cross the axis at negative values of R, which is the separation between the particles. We can look at the solution to the radial Schrodinger equation and see that, okay, because we've got this short range finite square well potential, the wave function turns over a bit quickly here, pulls a bit more weight of the wave function into short range, and then at long range it just goes away sinusoidally, or the potential vanishes, and then we just have a sinusoidally varying wave function. But again, this is the radial wave function here. So to get psi, we would need to divide this by R. Then we can effectively increase the depth of this attractive interaction to the point where we just introduce a new bound state. And then at this point, the potential has enough energy such that the wave function turns over and becomes completely flat at the boundary condition here. And that's where the scattering length diverges. So A goes to infinity. So if the wave function is really parallel with the, or is really flat there, the gradient is zero, then it's never going to cross the axis. So this is what we say when we say or this is what we mean when we say the scattering length goes to infinity. Basically, the wave function, or the long range, the start of this long range wave function is flat at the point where we leave this, or at the boundary condition here. But if we make the potential a little bit deeper again, we can support a bound state. So we have enough energy now that we can turn the wave function over. We've got a two-body bound state here, and we can produce real molecules. So this is effectively what's happening when we have a Feshbach resonance. This simple picture, it's I've left out some of the crucial details about hyperfine couplings, etc. But from a two-body perspective, this is essentially the picture we have, because we only ever see the long range, or in experiments, we only ever see really what happens at long range here. And so this tells us about the behavior of the scattering of the wave function, so the scattered state and the bound state at long range. Okay, so we can use the Feshbach resonance to tune this parameter A, and as we do so, this is the sort of thing that we're doing, well, this gives a picture of what's happening at the two-body level. So that sounds quite simple. We can understand that at the two-body level, but when we start to think about what happens in a many-body system, actually the behaviors get a whole lot more complicated and interesting. So if we look at taking these two relatively simple ingredients, being able to tune the interaction strength on the horizontal axis here, so this is the A parameter again, and also being able to tune the temperature on the vertical axis, we get a phase diagram that looks something like this. Okay, this is just a qualitative phase diagram. We know quite accurately what the phase diagram should be in the limit of fairly weak attractive interactions. So this is the BCS limit, where we've got a negative scattering length. And we also know how the system behaves in the what we call the Bose-Einstein condensate limit, where the molecules become so tightly bound that they start behaving like point-like bosonic particles. But this crossover region here, or this middle part of the phase diagram, is somewhat more challenging to describe theoretically, because we no longer have any sort of small parameters that we can use to describe the interactions, because the scattering length diverges here, so it's a strongly interacting system. And we have to understand, or we have to take into account correlations between many particles. And this is kind of interesting here, because we can reach a point where the scattering length diverges. So, and at that point, it becomes a length scale that's no longer relevant for the physics of the system, so it can become much larger than the mean interparticle spacing, etc. So at this point, the unitarity point, where the scattering length diverges, the only length scale that comes in is set by the spacing between the particles and the thermal de Broglie wavelengths. So there's really no longer any length scale due to the interaction, the S-wave interaction, or the S-wave scattering length doesn't come into the physical description anymore. So here, at unitarity, we get quite an interesting situation where only the density of the system and the temperature of the system set the physical properties, but it's still a strongly correlated system, so quite universal in that sense. So this is really, when we do our experiments, we like to do experiments here, because that's often the most interesting point for comparisons with theory. Okay, so that's a bit of an introduction to the system that we're studying, that we're looking at. I can show you some pictures of what the experiments look like at the end if anyone's interested, but I want to move on now to talk about the actual experiments that we're doing. So this is where we look at the first series of experiments is quenching from a normal fluid into the superfluid phase. So I showed you some pictures before in one of the first slides, where there were some experiments done using a temperature quench. So going from, so basically doing a rapid cooling from the normal phase to the superfluid phase. Those experiments studied the formation of defects. However, when you do a temperature quench, the timescales you can access are a little bit limited, because you're waiting for the system to reach thermal equilibrium. And the timescales for thermal equilibrium are typically on the timescales of hundreds of milliseconds or seconds in these systems. So that means the dynamics that you can study in such experiments are also limited to those relatively slow timescales. However, what we wanted to look at was a way to reach timescales that are faster and study dynamics that happen on shorter timescales. So our approach for doing that was, rather than doing a temperature quench, to do an interaction quench. So the basic picture that we have in mind, so I showed you this phase diagram before. The basic picture is that we want to start over here in the BCS regime. So we'll start in the normal phase with relatively weak interactions. I mean, actually still fairly strong interactions, but far enough on the BCS side of the Feshbach resonance that we know we're well in the normal phase, and we can sort of calculate or know the parameters of our system that we're starting with relatively well using kind of second order perturbation theory to describe the effects of interactions. Then we jump the interactions very quickly. So from here, we jump across to here. So we change the S-wave scattering length very quickly to this unitarity point where it diverges, where A goes to infinity. We're going to jump across there at a range of rates, at a range of speeds, and measure the subsequent dynamics. And so the nice thing about interaction quenches is that we can access timescales that are of the order of the Fermi time. So the Fermi time in our system is typically tens or 20 or so microseconds, and we can do our quenches in that same sort of time frame. So we can see dynamics that happen on much shorter timescales. And it turns out there's quite a bit that does happen on these short timescales, as well as the longer timescales. So that's the idea for our experiment. We start in the BCS regime in the normal phase. We jump across here to the strongly interacting regime. And because, well, depending on how much the temperature changes when we go from here to here, we should, or we hope that we're going to end up below this superfluid critical temperature, TC, and we'll be able to observe what happens when the superfluid forms. So here, we know that we're starting off in the normal phase out here. We don't expect the fermions to pair up, but as we cross into the superfluid phase, we know that in order to form a superfluid, these fermions have to pair up, and those pairs are what go into making the superfluid. So this is the sort of thing we want to study. Okay, so experimentally, what does that mean? Well, I've mentioned that we can use a what's called a Feshbach resonance to tune the interactions via this scattering length parameter. But the way we control, or the way we use a Feshbach resonance is basically by controlling an external magnetic field that we apply. So we have a large magnetic, or we have some coils just outside our experiment, and we can run currents through those to produce a magnetic field that the atoms feel. Once we've cooled them down, they can, and by varying the current, we can vary the magnetic field that the atoms experience. And so what we're going to do here, so for the particular Feshbach resonance that I'm using, or that I'm talking about today, we can start off, if we set the magnetic field at 800 Gauss, that's into the BCS side of the phase diagram. The pole of the scattering length, or the point where the scattering length goes to zero here, is at 690 Gauss. So for the experts, I'm using what's called a 1-3 mixture. So I'm using not the usual combination of, or not the most common combination of lithium hyperfine states, but probably the second most common combination. So what we do here is we're going to start off at 800, a field of 800 Gauss. We're going to ramp down to 690 Gauss, or the unitarity point. We're going to do that in a time that I'll call TQ, or T quench. And then we're going to hold the cloud at that magnetic field for some time, and then we take a picture of it. So if I do that, so that I should mention that actually our cloud is trapped in a potential that's kind of oblate shaped. So we've got a round cloud of atoms, but it's sort of flattened down, and we're going to look at the atom cloud from the top and take pictures of it from the top. So this this next picture will show you what, or shows actually a movie of what we see when we do this experiment. So we basically jump the magnetic field, hold hold the field at unitarity, and take images of the cloud in the trap looking from the top. So here, the first thing you might notice is it doesn't look like very much is happening at all, which is actually kind of what we expect. So here we're looking from the top at a cloud that's in the trap for different hold times. So the hold times here are going up in sort of, starting off at below a millisecond, then up to tens of milliseconds. And this is actually quite a fast quench here. So we're doing things we're quenching at 50 microseconds. And at first glance, it looks like not very much is happening here. But actually we know there should be quite a bit happening here. So we're starting off with a system that's in the normal phase, quenching it into where we expect it to be in the superfluid phase. What we expect to be happening is that pairs should be forming, the system, the momentum distribution of those pairs should be evolving and forming a condensate, and we should be able to see that. But it turns out when we look at a cloud in the trap at unitarity, it's very difficult to see any of the underlying dynamics. So we have to be a little bit cleverer with how we probe the system to get a picture of what might be happening there. So it turns out that there is a way that we can see a bit more and learn a bit more about what's happening. Particularly, we can look at what's happening to the pairs and the momentum distribution of the pairs, which is where we expect the interesting dynamics to be happening. So what we're going to do now in the next sequence is, instead of just ramping down, holding at 690 Gauss and taking a picture of the atoms while they're in the trap, what we'll do is we'll turn off the trap, ramp the magnetic field quickly into what's called the BEC regime. So we're going to, this is known as the rapid ramp technique for experts in the field, and this is what was used in some very early studies of the Fermi gases in the BEC-BCS crossover by Debbie Jin's group and Wolfgang Ketterle's group in the early 2000s, where they showed that these systems actually do produce a condensate of molecules, and has more recently been extended using or in Selim-Joachim's group to show how you can extract the momentum distribution of the pairs. So basically what we're going to do is we by ramping the magnetic field quickly into the BEC side, we take these pairs or these relatively weakly bound pairs that might be present at unitarity, project those into tightly bound molecules. And also, by going to this low magnetic field, these molecules begin to, or have a much weaker interaction with other molecules. So we can turn the trap off at that point, and or we turn off the optical part of our trap, which means that the cloud expands vertically, but it's expanding into a magnetic, harmonic potential in the radial direction. So it's sort of expanding a bit this direction and then just oscillating in a harmonic potential. And if we wait for 1/4 of the period in this harmonic potential, then we'll actually, whatever the spatial distribution was, will be projected into the momentum distribution, or the momentum distribution is what we'll observe after a 1/4 period of the oscillation in the of expansion into this harmonic potential. So that was perhaps a little bit of a complicated expansion, but explanation of what we do with this expansion, but I can explain it a bit more clearly later if anyone has questions. But the idea is we take our cloud, we turn off the tight confinement, ramp quickly to quickly convert our pairs into molecules, let these pairs expand, then take a picture and get the momentum distribution of the pairs. Okay, so that's the idea of what we're gonna do. And so this slide now shows what happens when we do the same experiment. The video on the left is this new way of doing the measurement. The picture, the video on the right is exactly the same one that I showed you before. And this is showing images at the same, so this is when we measure the cloud in the trap, we see nothing on the right here. But when we do this rapid ramp and then time of flight expansion, we can see that there is some dynamics happening here when we look at the momentum distribution of the pairs. So what we can see happening is that at very short times, actually, we don't see much change at all. So if you look at the very first image, so that one basically looks the same as what we had before we did the quench. But then very quickly, we start to see this bright, high density peak appearing in the center of the distribution. And that forms and becomes sharper as we hold the cloud for longer and longer. And so what this is showing us is actually the formation of a pair condensate. So when we cross the transition from a normal to a superfluid, we expect the pairs to be formed and then they condense into the zero momentum state and form a Bose-Einstein condensate of pairs. And that's what we can see happening here in this movie. Okay, so even though we can't see it when we look in situ, we can see that it's actually happening as expected here. So this is gives us a nice insight into the dynamics here. So, all right, so it's great that we can see kind of qualitatively what's happening with this movie, but actually we want to do some more quantitative analysis here, and we can do that by essentially taking these profiles, integrating over one dimension, and starting to look at the distributions that we see here and fitting to try and do some analysis, etc. So what we do, or when we do this integration, we see that what we find is that actually for all hold time, so this is following a short quench, this is following that 50 microsecond quench that I showed you previously. For all quenches, we find that we actually have a fairly Gaussian looking wing or wings in the distribution, so that there's these pedestals for all hold times. We get this nice Gaussian wing, and this is what we expect for a thermal distribution of atoms. So we can fit the wings of the distribution. So just looking at the part outside these dashed lines, we fit a Gaussian to those, and then we can see that on top of that Gaussian, as we hold for longer and longer, this peak appears in the middle here. And so this is a cloud of fermions, and this is, we're looking at the momentum distribution here, but seeing a peak of atoms in the middle of the momentum distribution means that we must be producing pairs, and those pairs are bosonic because we can't put more than one fermion in a single state. So this non-Gaussian peak that we're producing in the middle must be a result of pair formation, because there's no degrees of freedom for the fermions to access. But if we have bosonic pairs, those pairs can start to occupy low momentum modes, and we can have more and more pairs building up in the low momentum modes. So we can see also that not only is that momentum distribution changing as a function of time, it's also getting sharper and sharper. And by 100 milliseconds, we actually get quite a nicely, looks like a nicely defined bimodal distribution here, where we associate the middle or the sharp bit of that as a Bose-Einstein condensate of pairs. And we don't, beyond times of 100 milliseconds, we don't really see any further dynamics. So we can look at, so just saying if we can see that the area or this part that's appearing in the middle of the distribution is due to pairs being produced, we can look at the area, so this shaded area here on the slide of the distribution, so this non-Gaussian area, say that that's the paired component, and look at how that evolves in time. And what we see is that, so if we look at a very fast quench here, so this, again, the 50 microsecond quench, we can see that we start off essentially with nothing, Then by about 200 microseconds, this builds up very quickly. And okay, there's a little bit of an oscillation here. This is actually going to be the topic of the second set of experiments that we do. But then it's pretty flat once we get to a millisecond or a couple of milliseconds. It's basically flat and stable. And so this tells us actually that the pairs are being produced very rapidly. So in this kind of 200 microsecond window, the majority of the pairs are formed. And we can think about, well, what are the timescales that relates to? So this, if we think about these experiments being performed in a harmonic trap, where with timescales of the order of milliseconds, this is dynamics that's happening on much shorter timescales. So this is really being set, or the pair formation is happening on the microsecond timescale, which has to be connected to the Fermi timescale. So in the center of the trap, that is the densest, the part where the density is the highest, this Fermi time is around about 26 microseconds. So it looks like pair formation is happening on the timescale of several Fermi times here. Then as we do slower and slower quenches, we see that actually the pairs have already formed once we get to a quench time of about a millisecond or so, or be a couple of milliseconds. So these points here at 2.5 milliseconds, basically the pair formation has completely finished by the time we've finished the quench. So actually pair formation seems to be able to follow this almost adiabatically at this time scale. So things are happening quickly in these systems is what we can conclude. If we look, however, at the dynamics of or the shape of this non-Gaussian peak that we have on top of the pair, just the paired component that sits on top of the Gaussian. So we subtract the Gaussian from our distributions and look at what's happening there. You can see that even though the area is staying roughly constant, the shape of the distribution is changing quite a bit. So 200 microseconds after the quench, it's quite broad, triangular looking. Then by 5 milliseconds, it's starting to develop a bit more of a peak. But then after a second, we've got a very sharp peak in the middle. And this sort of narrow peak is what we expect for a Bose-Einstein condensate of pairs. So even though the pairs form quite quickly, that is the area under this of this non-Gaussian component is fairly stable after about 200 microseconds. We still need to wait several tens of milliseconds before the pairs have found their kind of equilibrium momentum distribution. So actually, I think what I might do is I'm going to skip over this part here, which just looks at the essentially the dynamics for reaching the pair distribution to reach its equilibrium. And also I'm going to skip over the adiabaticity part, but suffice to say that we can see by looking at the temperature after the quench, once the cloud has fully equilibrated, we can see how long we need for the quench to be adiabatic. And it turns out that once the quenches are longer than this few milliseconds time scale, they appear essentially adiabatic. Or close to adiabatic, but for quite faster quenches, the temperatures we reach are much higher. And so this adiabaticity, or to be adiabatic with respect to the full thermodynamics, we have to do it on timescales that we have to do quenches slower than the timescale set by the harmonic confinement. Furthermore, we can learn about the contact, but I'll skip over this part in the interests of keeping to time. And if you want to ask about that, I can answer questions about that later. But I want to spend the last few minutes talking about some recent experiments that are a bit preliminary, but looking at the amplitude mode of in these systems. So this is work that's not published yet, but we're currently trying to understand. So, or we're currently performing new experiments on, but I always like to share the new results and things coming out of the lab. So in systems like superfluids, superconductors, etc. One of the features of these systems is that when we go from a normal state to a superfluid state or a superconducting state, we cross a phase transition, and that crossing of the phase transition involves breaking some sort of symmetry. So when we form a superfluid, the superfluid order parameter that we form, or this wave function, if you like, that describes the superfluid, can usually be written in a macroscopic form. So it's written as some sort of complex function, which has an amplitude out the front and also has a phase term. And so both the amplitude and the phase may be functions of position or functions of time. But one of the features of these of superfluids or systems with a macroscopic order parameter is that we can write them in this way. And it's been known since the 50s or since the late 50s that when you have such a spontaneous symmetry breaking, there are different sorts of collective excitations that you can generate in these systems. So there's two types of mode. There's a Goldstone mode, which is corresponds to changes in the phase of the order parameter. So I should say actually that this kind of it's often referred to as a Mexican hat-shaped potential, but it's basically a plot of the free energy that comes from the Ginzburg-Landau equations for superconductors. But I'm not going to go into the origins of where this free energy curve comes from. But essentially, it supports two types of collective excitation. So there's this Goldstone mode, which corresponds to rotations in the phase of the order parameter. But also there's what's called the amplitude mode or the Higgs mode, which corresponds to oscillations in the amplitude, so the radius or the distance from the origin here of the order parameter. So it's basically here you can see it's oscillating in a curved part of the potential. So it does these oscillations must have a non-zero energy associated with them. So these are called gapped excitations. So we need a certain amount of energy to excite these. And in fermionic superfluids, we need to basically have twice the pairing gap worth of energy to produce this excitation. Again, I'm going a bit quickly over this, sorry, but I want to say that these are two sort of fundamental types of collective excitation that you expect in systems with spontaneous symmetry breaking. Okay, so the Goldstone mode in cold atom systems has been studied quite a bit. It's actually just a phonon mode or a sound wave, which has been studied firstly in some very nice experiments from Nir Davidson's group in Israel, and also earlier work in the Kedley group at MIT. But these experiments here really measured the dispersion relations, showing the expected Bogel-Yubov forms. And then some experiments in our group, the MIT group of Martin Zwierlein and also Henning Moritz's group in Hamburg, have looked at sound excitations in strongly interacting Fermi gases. The Higgs mode has also been studied in cold atom systems recently. So some very nice experiments from Emmanuel Bloch's group looking at the amplitude mode in a two-dimensional gas in an optical lattice in the vicinity of the superfluid to mod insulator transition. And also some very nice experiments from Michael Kerl's group in Bonn, looking at essentially driving the system at a frequency corresponding to the Higgs mode and seeing heating and seeing the effects there when the system's driven, showing up as a reduction in the condensate fraction, and using that to measure the excitation frequency. Our approach was actually to studying this is a little bit different. So we're going to use a smaller quench here. We're going to start off in the superfluid phase, again, a little bit to the BCS side, but well below the critical temperature, and jump the interactions to unitarity. Okay, and the reason we want to do this is basically sort of motivated by a prediction from Robin Scott and Sandro Stringari back in 2012 that says, if you do a sudden change of the interaction parameter, so the scattering length, you should also expect to excite this amplitude mode. So we've thought about this idea, and we discussed it with some theorists, so Victor Calusi, Servas Koppelmans, etc., and their team in Eindhoven. At the time, they were in Eindhoven, and they said, yeah, we can calculate what you might expect for the sort of ramps that you can do, and you can see that actually, if we look at the order parameter or the gap here, we expect to see this damped oscillation following the sort of experimentally achievable ramps that we can do here. So this looked very promising to us. However, these calculations are at 0 temperature and for a homogeneous system. So there's a couple of complications that we need to overcome in the experiment to be able to see this. So we said, well, what we can do this rapid ramp technique, which allows us to measure the kind of condensate fraction for a different, as we can do that as a function of time after we ramp, but that unfortunately integrates over the full cloud. So they were able to account for this theoretically and say that, yes, okay, well, you will still see some oscillation if you do this rapid ramp technique, but the oscillations are going to damp out much more quickly than if you could do it on a homogeneous system. So that made us a little sad. But then we remembered that actually we have a nice way to probe a cloud locally using one of our favorite experimental probes, which is Bragg spectroscopy. So the idea of these experiments is that we have a large atom cloud. We send in 2 focused laser beams. Those laser beams intersect in the middle of the cloud. So they probe a volume of the cloud where the density is almost homogeneous. And we can tune our Bragg lasers to kick out or to basically selectively excite pairs that are in the cloud which have 0 momentum. So we've seen in previous experiments that the Bragg spectroscopy is very sensitive to whether or not we have a pair condensate. So we should get a Bragg signal that's proportional to the condensate fraction, but we can do it locally in the middle of the cloud. And in fact, we sort of did a quick test experiment to see that, yes, the Bragg signal that we measure from the central part of the cloud does seem to go, or does seem to vary almost linearly in part of the range with the condensate fraction there. So this gives us a way to probe the cloud locally, where we expect that hopefully we should see this amplitude mode a bit more cleanly. So we tried some experiments where we do this quench, then apply a Bragg pulse and measure the Bragg signal for various different hold times to see what we see. And it turns out that indeed we do see quite a nice clean oscillation of the Bragg signal. We've done it we've run these experiments for a few different temperatures. So for cold clouds with a relatively large condensate fraction after the quench, and then for slightly higher clouds. And in all cases, we see quite a clean oscillation, but the frequency of this oscillation seems to change a bit as we get to smaller and smaller condensate fractions. So I want to emphasize that this is still very preliminary data, but it's enabling us to try and put together a picture of the pairing gap at unitarity versus temperature. So when we convert our measured oscillation frequency, basically twice the frequency of the amplitude mode, or half the frequency of the amplitude mode, normalized to the Fermi energy, we see values that are coming out about where we expect. So previous measurements of this, we've got a gap of about just under half of the Fermi energy, and we're seeing something fairly similar here. We only have a good measurement at fairly low temperature here, but actually from what we've been able to measure, the gap looks very stable and very constant until we get close to the critical temperature here, which is about 0.17. I want to emphasize though that these data are very preliminary and so still subject to some change. We've also looked at how the oscillations decay as a function of time, and so we can fit. They're expected to decay via a power law in the BCS limit. This exponent is expected to be 1/2, and in the BEC limit, it's expected to be 3/2. The decay coefficients that we fit so far seem to lie somewhere in the middle, but I do emphasize they have quite a large error bar on them. So this is still work in progress, but hopefully we're getting a picture of how the pairing gap evolves as a function of temperature in these systems now. So that's the new results that we're working on currently. So I think I'm pretty much out of time now, but I'll summarize there that we can learn a bit by looking at the dynamics in these systems following an interaction quench. And yeah, as Peter mentioned, we're also setting up a new lab, which has been taking up a bit of our time, but also been a bit slowed by lockdowns and not being allowed in the lab here. So that's been a frustrating time in the last 2 years. But I'll finish with a picture of thanking my team, so particularly Paul, Andrew, Alan and Ivan here, who've done a lot of the work of the experimental work that I've talked about today. And given the times that we're in, I've been forced to update my profile picture that's something more representative and probably what I look like this morning here. So thanks very much for your time and having me on to talk about this stuff. Happy to take any questions.
Yeah, thank you so much, Chris, for sharing all these exciting new results with us and for this very colorful and entertaining talk. So it's time for a couple of questions, but I know some of you have to go to other classes, and feel free to go at this point. Otherwise, we can continue discussing and take some questions. Any questions from the audience?
Yeah.
Yeah.
Stand up.
Yeah.
So there seems to be this in the phase transition. It's like if you have a gas of fermions, and then they transition so that they pair up, and you get this gas of bosons. Like, why does the transition? As far as I understand, you create a superfluid because nearly every fermion has paired up, and so now you have a gas of bosons. It seems like because of thermal excitations and all these things, there would be some portion that stays electrons and only some of them pair up. Why is it a complete transition across the boundary?
That's a good question. So I guess I should say that maybe I can. So when we cross the superfluid transition, the superfluid fraction doesn't immediately go to 1. The superfluid fraction might be a bit less than 1. Actually, the superfluid fraction and the condensate fraction are two different things here. So because we've got strong interactions and strong correlations, I mean, it's not exactly the same as liquid helium, but if you know the example of liquid helium, it can have a superfluid fraction of 1, but a condensate fraction of 0.1 or something like that. So that's a very different system to what I'm talking about here, but it's just using as an example that the condensate fraction that we measure here is not the same necessarily as the superfluid fraction. So the superfluid fraction in these systems we expect to be actually reasonably close to 1 once we get a bit below TC. So for some of the coldest temperatures, even when I measure a condensate fraction of say 0.5, the superfluid fraction should be relatively close to 1. Again, because the superfluid fraction is really about what are the allowed excitations in the system, and you know, do you have the energy to break pairs to start dissipating energy and so on, or can you produce thermal phonons in the system? They're the sorts of questions that decide whether or not you have a superfluid, whereas the condensate fraction is really just looking at how many pairs we have with zero momentum. So there are, I think, probably there are a number of subtleties in the answer to your question that are actually also not quantitatively well known, I would say, in these systems. So we know that we don't expect the condensate fraction and the superfluid fraction to be the same. And you know, there's been some investigations of things like second sound in these systems to try and get at the superfluid fraction. But yeah, certainly just as we cross the transition, we don't go from having zero superfluid fraction to having 100% superfluid fraction, but we do build up, you know, we do build up close to a full superfluid fraction. But as I say, that's different to the way the condensate fraction evolves. I don't know if I don't know if that's really helped answer your question, or if that's.
Yeah, it's helped me understand what my question is more, certainly.
It's a good question, and there's a lot of things we still want to be able to say. Well, quantitatively, we know that the superfluid fraction is this, but the condensate fraction is that, and you know, have like quantitative you know, answers to these questions, which we should be able to get with better experiments and, you know, better. And we certainly have some good theoretical guidance, but there's still, you know, some disagreement among theories about how these things should evolve with temperature. But yeah, the picture's starting to sort of solidify a bit more now.
Thank you.
Any other questions? Maybe I've got a quick question. Michael, you can check if there's anything in the chat. So my question would be, oh, Brian Salmer's got a question too. My question is very quick. When you do the Bragg spectroscopy, right? In your plots you have COM. Does that mean you measure the Bragg spectroscopy by the center of mass, the sloshing motion after applying the Bragg peak? Because you're still in the strongly interacting system. Otherwise, you would have to turn the interactions off. Okay.
Yeah, that's right. So what we do is we apply the Bragg pulse. That starts that transfers some momentum to the cloud. So it basically kicks some atoms, but because the system is still strongly interacting, those atoms that we've kicked may collide with other atoms in the system. So it's not like we get a Bragg scattered cloud that appears over here after we wait some time of flight expansion. After we do some time of flight expansion, basically we just smear out the whole cloud because there's many elastic collisions that can happen after the Bragg pulse. Mm-hmm. However, as we know from first year physics, that elastic collisions preserve the total momentum. So as long as you measure if you do a measurement of the center of mass position after the Bragg pulse, so you basically integrate the cloud, evaluate the first moment of the cloud after some expansion time, and then compare that to the first moment of the cloud without the Bragg pulse, you can still determine the momentum that you've transferred to the cloud without having to worry about, you know, the effects of these elastic collisions afterwards, because, you know, the momentum you've imparted is preserved. So you still get that quantity that you're trying to get.
Yeah.
And so that's why we plot center of mass displacement as our variable, which after a time of flight is proportional to the momentum we transfer. So when you think about Bragg from the point of view of linear response theories, then you normally think about how much momentum you transfer or how much energy you transfer, and that's a way to get at the momentum transfer.
Yeah. Thank you, Brian Sam.
Yeah, Chris. First of all, I just want to say that was a marvelous talk. I learned a ton, and I also appreciate the fact that you were willing to share like latest results that aren't, you know, readily publishable yet, but, you know, this is what's going on right now. I have a very different question just from an experimental point of view. I'm curious as to how you change hundreds of Gauss magnetic fields in 50 microseconds.
Yeah, good. You need postdocs who know how to make good electronics and deal with dissipating large back EMFs and with potentially very high currents. So essentially, yeah, we have a lot of high-powered protection diodes and things in there, but MOSFET banks, so banks of large banks of MOSFETs, heavy water cooling, and high-powered Zener diodes to deal with the back EMFs and so on. So yeah, there's quite a bit of electronics engineering that goes into that. So we try and minimize the inductance as much as possible in our coils, but it's still, when you're producing hundreds of Gauss, you still need, well, I think tens of microhenries is optimistic, maybe like 100 or so microhenries is what we've got as the inductance in our coils. So it's not a negligible inductance to deal with when we're sending currents of 100 or so amps through them. So yes, it's challenging, and that's probably why these experiments took a while to actually do before we could really switch the currents in such a way that we didn't get large back EMFs or eddy currents in other places of the experiments as well. So there's lots of technical things you have to take care of when you're doing those sorts of experiments. It's an experimentalist question, all right, but yeah, it's a very real thing we have to deal with.
Excellent, thank you.
How broad
if you're interested, we can share, how we share circuit diagrams if it's actually of interest to you.
Very cool.
How broad is the resonance? Like how precisely have to fit the endpoint then?
Good question as well. So the 690 Gauss resonance in lithium-6, it's not as broad as the 832, but it's about half as broad. So I think the width is the width parameter for the Feshbach resonance is about 140 Gauss or so.
Okay, yeah, so
it's still a broad resonance. So if we get within 0.1 or 0.2 Gauss, then we've done extremely well. That's that's the last of the uncertainties that we need to worry about. That's one of the advantages of the broad Feshbach resonance, is that means it's a lot more forgiving for the precision of your magnetic field.
So Chris, unfortunately, we have to clear out this room for the next class. However, Michael is co-host of this of the Zoom call, so he will actually keep the call open and you can discuss a little further. But at least for us who are actually still here, we unfortunately have to close it for today. I would have loved to talk much more to you, but I'll see you around at some point anyways.
So I hope so, yeah, that'd be great.
Yeah,
thank you.
Thank you so much for the talk. And then we will zoom out here, but Michael can keep the discussion open. All right, thank you. See ya.
Thanks very much, bye.